Okay, so good evening everyone and welcome to the 10th session of this course Measure and Integration. Today we'll be talking about Radon-Nikodym derivative and then we'll go to LP spaces. Okay, so let us see what the Radon-Nikodym theorem is. Okay, so far what you have seen that given a measure space X is mu, and if you have some non-negative integrable function, okay, so what does this mean? This simply mean that this f mod f d mu is finite. Okay, so that's all what we mean. So since it is non-negative, so we'll say that f d mu is finite. Okay, so if it is given that you have integrable function over this x, then if you define a new function that is new on the set S, okay, so if you define this new like this, okay, given by this quantity, okay, then you have already proven that this is a measure. So you have shown that this is a measure, and in fact what you have shown that this new measure new is absolutely continuous with this new with mu. Okay, so this new is absolutely continuous with respect to mu. This we have seen in the last session, I guess. Okay, so what you have seen that if you have this, so if you have this excess mu, any given, it is given to you, and if you from here, if you define nu like this, okay, so nu of E equal to f d mu, then what you have shown that this nu is absolutely continuous with respect to mu. Okay, now the other question is, is the converse true? Okay, so this is the conclusion. So from here what you have defined that you got that nu is absolutely continuous with respect to mu. Okay, now the question is converse. Suppose if you have two measures mu and nu, and suppose they are, so the question is like this, that suppose if you have two measures mu and nu, so how this nu can be written? So suppose you have been given this mu and you know that this nu is absolutely continuous with respect to this mu, then can you say something about this nu? Is it possible? So Radon-Nikodym theorem says that in fact it is possible, and the form what you will get is like this. Okay, so there will exist some function f such that this will happen, but there are certain restrictions. The restriction is that the measure should be sigma finite. Okay, so the measure what we are considering should be sigma finite. Okay, so this is our goal. So not goal, but this is the theorem what it says. Okay, so precisely we have the following theorem. So this is the first theorem. So I mean the general one would come in the next slide. So what this theorem says, that suppose you have a finite measure space. So this is dealing with the finite measure space, and okay, so and you have another measure which is nu, and this is also a finite measure space. Okay, so finite means basically that nu of x is finite. Okay, so this is also finite and this is also finite. Okay, and suppose that this nu is absolutely continuous with respect to this mu. Okay, then what the theorem says, that there will exist a non-negative function. Okay, so non-negative function f, so non-negative function f defined on x. So there will exist a function f from x to 0 infinity, okay, such that which is integrable with respect to mu. Okay, so integrable with respect to mu means that f d mu is finite. Okay, so there will exist a non-negative function which is integrable, okay, such that this nu what you had, this nu can be written in this form. Okay, so for finite measure space and finite measure nu, you have this theorem which is sort of converse of what we have seen so far, right? Okay, so this was the first theorem, and it says that this f will be unique. So the function what we are getting here is unique. Unique means, I mean, there could be another function which is almost everywhere same as f. Okay, so what it says, that if g is another integrable function such that this happens, then this function f and g are actually same almost everywhere, and almost everywhere with respect to this mu. Okay, so this measure mu, so with which we are considering the integral. So you can understand that if f is equal to g almost everywhere with respect to mu, then this would imply that this nu of E is equal to f of d mu is equal to g of d mu, right? Because f and g are almost everywhere equal with respect to mu, so this integral will be same. Okay, so this definition, I mean this quantity makes sense, that nu of E, right? Okay, so this is what this theorem says, and this is limited to this finite measure space. Okay. Okay, I hope this is clear to you. Okay, so now let's move to the next part of this theorem. Okay, so using this theorem, you can actually prove this one. Okay, so what this theorem says, that now we will be talking about signed measure. Okay, so here everything was measure means positive measure. Now we will talk about signed measure. Okay, so suppose you have a measurable space x comma s, and suppose that there are two signed measures, mu and nu, and both are sigma finite. So here we had this finite, now we are translating or shifting this theorem to sigma finite measure space, and the measures what we are taking is also not just a measure but signed measure. Okay, so this sort of generalization this is, so you have sigma finite space, measure space, and the measures are also signed measures and not just positive measures. Okay, so so if you have mu and nu, sigma finite signed measures, such that this nu is absolutely continuous with respect to mu, then there exists a measurable function f, okay, such that nu of E is equal to f d mu. Okay, so here also you have so here you don't have non-negative function, you have just measurable function. So in this theorem it was non-negative, and the reason being that this, that these measures are positive measure, so that's why the function what we will get should be non-negative. Okay, and here since we are dealing with signed measure, that's why this function is just a measurable function, need not be non-negative. Okay, so this is what this Radon-Nikodym theorem says. Okay, so here I think there is a typo, so this is for sigma finite. Okay, yeah. Okay, so these two theorems are, this is the most general theorem, so this is all what you need to remember, and this is just a particular case of this one. Okay, so now we'll just move to this concept of Radon-Nikodym derivative. Okay, so you have seen so far that if you have two sigma finite signed measures, so this is what it says, that if you have, so this nu and mu, let's say you have two sigma finite signed measures such that this nu is absolutely continuous with respect to mu, then what you have, what you get to know from this theorem, that there exists a measurable function f such that this happens, right? So try to look at this one, that nu of E. So if I want to write it in the just try to compare with this one. So suppose y of x is equal to some a times x and f y dy, right? Okay, so I should not write f, but let me write it y and here t. Okay, so now you know that dy by, okay, so yeah, dx will be f of x, right? So let me just make it more okay, so let us call this, so this d m1 of t. Okay, so this is just a Lebesgue measure. So what you get is, how should I write? Okay, maybe I'm just trying to make you understand what this derivative is. Okay, so let me write dt. Okay, so far. Okay, so this is at the Riemann integration as of now. So you know that dy by dx is f. Okay, and f is this quantity, right? Okay, or if you want to write it in this way, that would be better. So y of, let it be, yeah, Okay. Okay, so this is what you have. So this function, okay, this function ft is called derivative of y with respect to x. Okay, so this is the derivative, right? This is what you got here. In the same way, I mean analog to this one, what you have here, you see that this nu of e is some function, integration of some function with respect to this Lebesgue or some measure mu. In this case, this function f is said to be Radon-Nikodym derivative of this nu with respect to this mu. Okay, so this function f, what you are getting from this theorem, is called Radon-Nikodym derivative of this nu with respect to mu. Okay, so this is what Radon-Nikodym derivative is. Okay, okay, so this is, I mean, this is just to motivate you. Okay, so I mean, this was just to make you understand that how this notation is coming. Okay, so this is coming because of this fundamental theorem of calculus type of result what you have seen. Okay, okay, so now we'll see some examples how to compute this, okay, in the coming slides. So yeah, so this is what I have said here, that the function f, what you have seen, that the existence is guaranteed by this Radon-Nikodym theorem. So this function f is called Radon-Nikodym derivative of nu with respect to mu. Okay, and this is the notation to represent that. Okay, now okay, so now suppose you have a measurable space. Okay, so this is some sort of what do you say, that chain rule what you have, I mean something like that. Okay, so it's like chain rule. So what it says, that suppose you have a measurable space and let lambda mu be sigma finite measure. So just note it down that this is a measure, that means positive measure. So these are not sign measure. Okay, so suppose that you have lambda and mu which are sigma finite measures, such that this mu is less than or absolutely continuous. So mu is absolutely continuous with respect to lambda. Okay, and now assume that you have another sigma finite sign measure. Okay, so this is a sign measure. So suppose you have this nu which is a sign measure, and this nu is absolutely continuous with respect to mu. Okay, okay, one more thing, just try to note it down here, that when I say this nu is absolutely continuous with respect to mu, then you have this d nu by d mu equal to f, right? So the function which is absolutely continuous, I mean the measure which is absolutely continuous, that can be differentiable, I mean that is differentiable. So this nu is differentiable with respect to mu, so that's why you write d nu by d mu. Okay, okay, in the same way here you see this nu is absolutely continuous with respect to mu, and mu is absolutely continuous with respect to this lambda. So this, now just see this one. Okay, so I mean you can easily prove that this would imply that this nu is absolutely continuous with respect to lambda. Okay, okay. Okay, so this you will get, and from here you can see that this d nu by d lambda makes sense. I mean this can be defined by, I mean there will exist a function f such that this thing will be equal to this function f, that is guaranteed by this Radon-Nikodym theorem. So this is fine. In the same way, this nu is absolutely continuous with respect to mu, so this quantity is also, I mean, well defined. In the same way, this nu is absolutely continuous with respect to lambda, so this d mu by d lambda is also sensible. Okay, so these all three quantities are sensible, and these are guaranteed by this Radon-Nikodym theorem. This proposition, what it says, that if you have such a chain of absolute continuity, then you have this d nu by d lambda. Okay, so this d nu by d lambda, so the last two quantity is equal to d nu by d mu into d mu by d lambda. Okay, so this is what it says, that it is equal, and it is equal almost everywhere with respect to the last, I mean the last one, with respect to the lambda, measure lambda. Okay, so this is what this type of chain rule is there. Note here the main difference is that, the main thing to be noted that these two quantities are measures, and this nu can be a measure and can, or it can be a sign measure as well. Okay, so this has to be kept in mind that these two things what we are saying are measures. Okay, so that's all about this Radon-Nikodym derivative. We'll see some examples later on. Okay, I hope this is clear so far. Okay, so now let's move to this Lebesgue space. Okay, so far in some sense you have seen L1 space. Okay, so you'll get to know what L1 space is. Okay, so let me first start with some measure space. So suppose you have this measure space XS mu. Okay, and suppose you have a measurable function f defined on this space X, and this is measurable. Okay, and measurable with respect to this, this measure space. Okay, so that is, this is the underlying measure space. Okay, so this function is measurable. Now for p in 1 infinity, define this function. Okay, so you notice that this function p is a function from set of measurable space. Okay, so set of measurable function. Okay, and to 0 infinity. Okay, it could be infinity. Okay, so define this function. Okay, so this function is taking some function, measurable function, and the value what it gives is this one, that it is integral of this mod f raised to the power p and then over 1 by p. Okay, so in case p equal to 1, it is just the integral of mod f. So norm of f1, if you see, this is just integral of mod f, right? Okay, and if you go for 2, it will be mod f2 will be x mod f square and then 1 by 2. Okay, so this you have seen already, you have seen this sort of thing in this chapter of integration. So we are, some sense we are trying to introduce some other Lebesgue space which deals with integrals. Okay, so for p, when p is less than infinity, we have this formulation, we define this function, and for p equal to infinity, we defined in this way. I have introduced this concept also, I think, in some of the sessions earlier. I don't remember the session number, but I have introduced this quantity. So for continuous function, this is nothing but the supremum of the function, right? So what it says, that suppose you have a function f, so let me start with some continuous function. So suppose this is your function, okay, and in AB interval, this says that consider the set. So consider this set. Try to consider this set. Mod f greater than m means that mod of fx is greater than m x, such that, so consider this set. Suppose this m is this one. Okay, then saying that consider the points where fx is greater than m. So if m is this one, so this is my y axis, so this is my m. So you have to consider those points where the function is taking value greater than m. So these are the points where, corresponding to this, these are the points where the function is taking. So this is not a well defined function, so let me make it more. Okay, yeah, so yeah, so this is my m, so this length. So these are the points till here, where the function is taking value greater than m, right? So this is the set, right, for this m. So let's say this is m1. Now choose this. So this is, let's say this is the maximum value. Let me draw this function. Okay, now consider this as your m, which is the supremum of this function, right? So suppose this is m tilde or m2. For this m2, consider the x such that f of x is greater than m2. Then what will be this set? This is phi, right? Because there is no point where function is taking value greater than this. So this is phi. So mu of this set will be 0. If you take any number which is less than this measure will be positive, right? If you see this quantity, so if you take any point, like if you choose any point in between here, less than m2, you will see that the measure of the set will be not 0, it will be some positive quantity. But for this value of m, you can see that this is 0. Okay, so you have to choose now you choose any other point which is greater than this as well. So choose this m3. Okay, now you can see this m3 is this line. Now consider the set x such that mod of fx is greater than m3. Now this set is also empty, right? There are no points where the function is taking value greater than m3. So this is also the m3 is also point where the this measure of that set is 0. So consider, so you can see if I consider this point, then it will be m2 comma infinity, right? This set, I'm talking about this set, the set whose measure will be 0. So what I'm trying to say, that if you choose any value, so if you choose m greater than m2 or equal to m2, this would imply that mod f greater than m is null set, right? So what is the infimum of this set? Infimum of this set will be m2, right? Infimum of such m. So you have to choose the infimum value of the numbers after which the function is not taking any value. Okay, so that is the sort of, in case of continuous function, consider the supremum. Okay, so when you are dealing in a compact set, it has a supremum. So I am here considering compact set AB and I am taking a continuous function, that means it will have a supremum. If you take any point, any value larger than the supremum, then measure of that set will be 0, this set. So supremum would be the minimum value. So supremum would be, this will be, so if you start taking the infimum of such value, this will be the supremum of function. Okay, supremum or just f supnom, right? The infimum will be this. Is this clear or do you have any confusion? So for continuous function, you understood what I am trying to say, that this f infinity norm is nothing but the supremum norm for the continuous function. But the moment you choose some, any other function, just a measurable function, then there could be point where the function is taking value, not this one. So suppose this type of function, that at this point it has a jump discontinuity. I am just taking a discontinuous function. So you see, after this value m2, the measure, so this is a singleton point, right? This is x0. So the measure of just singleton x0 is 0. Okay, so in that case also this m2 will be, the f infinity. I was trying to make you understand through this graph, but I don't know, it's, the space was not that much, so I could just write in this fashion. So if you have doubt, you just ask me. That would be a better option, if you have not understood at any point.
M is defined the supremum norm.
No, what I am trying to say, that for continuous function, this f infinity, this quantity is equal to f supremum for continuous function. Okay, So why this infinity comes as a symbol, you will get to know. So why we are taking infinity. So that will be, I mean, this comes due to some reason. Okay, so what I am trying to say, that this f infinity is the supremum norm for continuous function. But for general measure, so for measurable function, you don't have this sup norm. I mean, you cannot define, you can define, I mean, supremum of some function, but that will not be a norm. Okay, so but this will be a norm. You will see this in a particular class of function. So overall, if you didn't get this, so what I can say as of now, that you, so did you understand this one, at least what I was trying to make you understand? What is this set? So let me write it again. I mean, that would be a better option. So what I am trying to say, so what is this set? Try to focus on this set. So this is x such that fx is greater than m. Okay, so you choose all m. You choose m equal to 0, m equal to 1, m equal to 3, I mean m equal to 0.25, anything what you choose. So try to look at this set. Okay, and you see what is the measure of this set. Okay, now when this measure is becoming 0, you consider such m. So suppose this is 0 for m1, m2, m3. I mean just 3 quantities. Suppose that, I mean it will be infinite, but for example, suppose that there are 3 numbers m1, m2, m3 for which the measure of this set is 0. Okay, now consider infimum of this m1, m2, m3. This will be called f infinity. I mean this is what this norm is. Okay, so this will be infimum of such m's. So this f infinity norm is infimum of all real number, all positive real number, such that the measure of this set corresponding to this m is 0. Okay,
Yes, sir.
now it's clear, right? The definition.
Yes, sir.
Okay, so so for p, I mean in this range, which is, I mean when p is finite and greater than 1, this is the quantity. So I am defining this is this some quantity, and for p equal to infinity, I am defining this quantity. Okay, now the function f, the measurable function f, what we started off with, this will be called p integrable if norm of this quantity is finite. Okay, you can clearly say that this is greater than equal to 0, right? If this is finite, then we say that the function is p integrable. So you remember that when this was finite, we said that f is integrable. Now since we are dealing with p, so we will say p integrable. Okay, and for the infinity case, we say that f is essentially bounded if this is finite. Okay, so these are the two terms what we have. So this p integrable and infinity, I mean essentially bounded for infinity. Okay, so these are the notions. So I will talk about whether this is a norm or not in upcoming slides. Okay, so far you just remember that these are the definition what we have defined. Okay, so now let us see some inequalities which are important, especially this Minkowski's inequality. So I'll tell you. So suppose you have this p is any number which is lying between 1 and infinity. Okay, then you say that p prime is conjugate exponent of this one if 1 by p plus 1 by p prime is equal to 1. Okay, if this is relation is satisfied, then we say that this p prime is conjugate exponent of p. So for example, if we choose p equal to 2, then what will be p prime? So it is 1 by 2 plus 1 by p prime equal to 1. So this implies that 1 by p prime is half. So this implies p prime is 2. Okay, so 2 is conjugate exponent of 2. Now you choose p equal to 3, then you will have 3 here. 1 minus 3 will be 2 by 3. So you will have 3 by 2 p prime. Okay, I mean these are some examples. Okay, now this is the case when p is lying between 1 and infinity. Now suppose p is equal to 1. In that case, you see, you will get 1 plus 1 by p prime is equal to 1. This would imply that 1 by p prime is equal to 0. So it seems that if p prime is infinity, suppose infinity is some real number, then we know that 1 by n, limit n going to infinity, is equal to 0, right? This sequential limit is 0. In that motivation, you say that p prime is infinity. I mean, this is not the actual reason, I mean, the actual mathematics, but what I am saying, that for p you defined in this way, when p is lying between 1 and infinity, you define the conjugate exponent in this way, and you define p for p equal to infinity, for p equal to 1, p prime is equal to infinity is the conjugate exponent. So this is the definition, okay? This is the conjugate exponent. So, or you can write it in this way, that infinity is conjugate exponent of 1 and vice versa. So of 1 and vice versa, that is 1 is conjugate exponent of infinity. Okay, so this is, I forgot to write it here. So we defined it for 1 and infinity, and for when p is lying between 1 and infinity, for p equal to 1 or p equal to infinity, you have infinity and 1 as the conjugate exponent, and this is the reason, I mean, the vague explanation what I can say. Okay. So this is what we mean by conjugate exponent. Now let's see what Young's inequality is. So it says that suppose you have this p is lying between 1 and infinity, and p prime is the conjugate exponent, then a over 1 by p into b over 1 by p prime is less than equal to a by p plus b by p prime. Okay, so I mean, just to make you understand, for example, you choose p equal to 2. So as I have shown you here, that when p is 2, p prime you can calculate that p prime is also 2. Then this inequality says that root of ab is less than equal to a by 2 plus b by 2, and you know that this is true, right? So if you rewrite this, this is nothing but 2 root ab, a plus b, and this is saying that a plus b minus 2 root ab is greater than equal to 0, and this is true, right? This is nothing but root a plus minus root b whole square, and this is true. So this is true. So I mean, this is just a particular example of this exponent. So you know this is true, and this is some sense generalization of that. Okay. In the so this was Young's inequality that deals with just real numbers, I mean a and b type of thing. But now we'll have a similar sort of, I mean, using this Young's inequality you can prove this Holder's inequality. And what this inequality is saying, that this is nothing but L. Okay, so let me not deal with L1. So what it says, that integral of mod f times mod g is less than equal to, so choose p, so p is given to you, okay, and p prime, so any p you choose between 1 and infinity, and p prime you choose as the conjugate exponent. Then if f is p integrable and g is p prime integrable, okay, then this fg is less than equal to fp and g p prime. Okay, so this is norm of fp. Okay, I should not say norm, but whatever has been defined earlier. So this inequality is true. Okay, so this is nothing but norm fg1. So it says that norm fg1 is less than equal to norm fp into norm gq. Okay, so I am saying this norm again and again, but this is not a norm, but under certain, I mean, when we redefine this set, it will be a norm. So as of now, I am saying this as a norm, but you will just understand what this is. I mean, so far it's just this definition, that's it. Okay, so far this is this definition, and that definition I am saying as norm. Okay, so this is saying that norm fg, one norm of fg is less than equal to p norm of f and p prime norm of g. Okay, so what it says, that if you have function f which is p integrable and g which is p prime integrable, so this p integrable means this is finite, p prime integrable means that this is finite, then it says that the product fg will be one integrable. That means this quantity will be finite because this is finite. Okay, so for example, what can I say? Just a second. So I mean, for example, what you can think of is, suppose we are in 0 1 interval. Okay, so you know that 1 by x raised to the power 1 by 4 is L2, I mean is in L2, I mean this 1 by x raised to the power 1 by 4, 2 norm is finite. Okay, so p is equal to 2, p prime is equal to 2. So suppose f of x is equal to g of x is equal to x raised to the power minus 1 by 4. Okay, so if you integrate this, so what is this 2 norm? So this f2, if you want to calculate, this is nothing but square of this function. So this is x minus half and then half, right? And it 0 1. So if you integrate it, what you get is x raised per half by half, then 1 by 2. So this is lying between 0 and 1, and then you take whole 1 by 2. Right? So this quantity is finite, right? This you know. So this f and g belong to L2. So p equal to 2 and p prime is equal to 2. Then this result says that if you multiply this function f and g, which is x raised to the power minus half, then this is in L1. Oh, so I should not write L1. So 2 integrable. Okay, so suppose f and g are 2 integrable, then this theorem says, or this result said, that the product f into g is 1 integrable or integrable. 1 integrable. Okay, so these inequalities are very helpful in studying this LP spaces. Okay, so you'll see the use later on. Okay, so far you just try to remember this inequality, that 1 integration of fg is less than equal to p integration of f and g p prime integral of g. Okay, and this is called Cauchy-Schwarz inequality for p prime equal to 2. Okay, and this is the Minkowski's inequality, and this is sort of triangle inequality. So you have seen triangle inequality for real numbers, that mod of x plus y is less than mod x plus mod y, right? So instead of this mod, now we have this norm, and instead of this real number we have measurable function. So this is what it says, that p integral of f plus g is less than equal to p integral of f plus g integral of p integral of g. Okay, so for p equal to 1 you can easily prove, right? So for p equal to 1, let us see. So norm of f plus g, if I say p equal to 1, so this is nothing but mod of f plus g and then d mu. Now you know that this I can, so this you know that f of x plus g of x, these are not real numbers, right? So this function f is defined from x to r, so these are real number. So you can use triangle inequality here. So this is mod of fx plus mod of gx, right? So let us deal with just this Lebesgue integral. So this is d of x, and this is fx plus gx. Now you can split this using triangle inequality, so you will get fx dx plus gx dx, and this is nothing but a 1 norm of f plus g norm of, 1 norm of g. So this is just for just one p equal to 1, but for any p between 1 and infinity, and in fact at infinity also you can prove this thing. Okay, so you can prove this type of Minkowski's inequality. Okay, now because of this, see what this says. This says that suppose your f is p integrable, g is p integrable, then it says that f plus g is also p integrable, because f is p integrable means this is finite, g is p integrable means this is finite, and this quantity is less than equal to this plus this, so this is also finite. right? So this inequality tells you that if you have two p integrable function, then the sum of that is also p integrable. So if f and g are p integrable, f plus g is also p integrable. Okay, so this is what this Minkowski inequality is telling. And you can also show that if f is p integrable, and if you multiply by some real number or complex number alpha times f, then this is also p integrable. Okay, so this space of p integrable function, okay, so the space of p integrable function for p lying between 1 and infinity, or essentially bounded function, that is f belonging to, the space, I have not defined what this space is, so I have written it here. So x of p, okay, so let me denote it this by this. So x of p is set of, so let me write in two parts. So when p is between 1 and infinity, okay, so in this case we defined this norm as integral. So consider the function, so f belong to xp if and only if norm of fp is finite. Okay, that means it is p integrable. But for p equal to infinity, f belong to x infinity if and only if norm of f infinity is finite. Okay, so these are called essentially bounded function. Okay, now this xp space for each p is a vector space. That means if you have two functions, the sum is also, there are many things to check, but at least you know that this is closed under addition and scalar multiplication. Rest of properties can also be proven. Okay, but I will not prove this thing, but you can check that this xp will form a vector space over the field C or over the field R, whatever you are concerned with. Okay. Okay, so is there any doubt so far? Okay, if there is no doubt, then maybe we can proceed. Okay, now I was telling from that, since I defined this quantity, that it is not a norm. Okay, so what are the properties of norm? There are three properties, right? So one is that it should be non-negative. It should, there should be this triangle inequality should be satisfy this function. And the third one is that norm of, this function, so f is norm if and only if the first property is that f should be greater than equal to 0. Second thing is that f of x plus y should be less than equal to f of x plus f of y. And the third one is that f of x is equal to 0 if and only if x is 0. Then we say that this function f is norm. So here we define this quantity p from the set of measurable space, right? So let me denote by xp. So not just measurable for function. So okay, xp I have denoted it when these are finite, but okay, we don't need to consider this to be finite for defining this norm. So we can consider space of measurable function to R, right? So we have defined this one. So let me just write the definition again. So this is nothing but mod fp 1 by p, and so this was for p in 1 comma infinity, and this is the infimum of m greater than 0 such that mu of mod f m is 0. Okay, so these are the quantities what I defined above. So you can check that these are non-negative. This is just clear from here. This is by Minkowski. You have seen that. So Minkowski's inequality tells you about this. And if you see that if the function is 0, then obviously this integral is 0. and this is also 0. So f equal to 0 implies that this is 0, but the converse is not true, right? So if you know that if you define fx to be, let's say 1 when x is 0, and it's 0 when x belong to 0 comma 1, so you know that f of x, this mod of f over 0 1, so this integration is 0, right? Because it is 1 just at one point, so 1 point does not matter. So this is nothing but mod f dm1 over 0 1. So this is 0, but this function is not 0, right? So this norm, so it is saying that one integration of f is 0, but f is not identically 0. But you notice one thing, that f is 0 almost everywhere, right? So now what we'll do, we'll try to redefine this space xp. So this, on this space, this is not a norm on xp, okay? That is due to this reason. Now we'll define some other space using this xp. So xp, so far we have considered the space where the p norm is finite, or this function, I mean this is finite, that's it. Okay, so the set of measurable functions such that the p integral or infinity norm of f is finite, then we say that space to be xp. Now we'll define another space from this space. So suppose this is your xp. Okay, let me write it somewhere here. So suppose this is your xp. Okay, now let us define some of this, an equivalence relation on this xp. So xp is measurable function with this p finite. Okay, so this is what xp is. Now let us define some equivalence relation. So we say f is related to g if they are almost everywhere equivalent. Okay, so you have this xs mu as your initial measure space. So with respect to this mu, these functions are almost everywhere equal. Okay, so we say f is related to g if f and g are almost everywhere equal. Okay, that means that where the points where the function are not equal is of measure 0, so is null set. Okay, so you can check that this is an equivalence relation. Equivalence relation means that it is reflexive, symmetric and transitive. Okay, so that you can check that this is an equivalence relation. Notice one more thing, when I say f is equivalent to g, that means f and g are almost everywhere equal. Now so f is related to g means f is equal to g almost everywhere. This would mean that mod fp is equal to mod gp almost everywhere, and this would mean that the integral is same, right? You know that when f1 and f2 are almost everywhere equal, then the integration f1 is equal to integration f2, right? This you already know. Okay, in the same way, this mod of fp is equal to mod of gp. That would mean that the integral of mod fp and mod gp is same. So this means that fp norm is equal to gp norm, right? And for p equal to infinity also you can define in this way. I mean, you can check. So what it says, when f and g are equivalent, then the norms are same, right? Okay, so that's just a remark. Now you see, when you have an equivalence relation, you can define partitions, right? So this xp can be partitioned in different partitions, right? Like this, you can break this space in different partitions. Like the partition will say that this space, if you have f here, so let's say this is equivalence class of f. So this is f1, let's say this is equivalence class of f2, and so on. I mean, every class. So because this is an equivalence relation, you have equivalence class, and that equivalence class will partition the set xp. Okay, so these are the properties of equivalence relation. Okay, so So by definition, this f1 class will contain all the g belonging to xp such that g is related to this f1. So all function which is related to f1, that means related means g is equal to f1 almost everywhere. So if you have f1 any function, so all the function which is equal to this function almost everywhere is sitting in this class, I mean here. Okay, so now this is called one element of, so I am defining this space LP or x tilde p. Okay, I don't know why I have written this x tilde p. Okay, so I am defining this LP afterwards. Okay, so actually here also I don't know. Yeah, okay, so when I am saying xp, okay, so I am not taking these conditions. Okay, so from my notation I am saying xp is just measurable function space. I don't know, this does not make sense defining xp, so you can consider this as finite, I mean that's fine. Okay, so this x tilde p, instead of this x tilde p, just write directly LP. Okay, so LP is the set of all equivalence classes of this sort. Okay, now notice one thing, that this equivalence class, so suppose you choose one function that, now try to understand this point here, that this LP space does not contain any function, it contains a class of function, right? So this whole class is one element of LP. So this LP is collection of this f, okay, such that f belong to xp. So this is what LP space is. Okay, and xp is this one, that measurable function with norm of p finite. Okay, so this is the LP space. Okay, so I mean I have written it again here. So okay, I mean you don't need to consider this. I was trying to define it in two steps, but I mean I can define it here as well. Okay, now try to understand what the norm we are giving. So now this is not a function, this LP is not a function, but it is this whole class, right? This is a bigger part. So for example, if you consider this function f of x equal to 0 for x belonging to 0, 1, and you consider this function f, so what I defined here, f1 of x is equal to 0 if x is 0 and 1, and it is 0 when x is in 0, 1. Now you see these two functions are almost everywhere equal. So now this is belonging in one class. Okay, so this is belonging to the 0 class, and 0 means this class of f. Okay, so both f1 and f2, so f1 comma f2 belong to the 0 function. So this 0 class or f1 class, or let me define it in this way, so define it in this way: 2 when x is equal to 0 and 0 when x is belonging to 0, 1. So you see this f1 and f2 are almost everywhere same, and f1, f2 belong to the function f, where f is identically equal to 0. So f1, f2 and f all are together in one class. Okay, so that's the difference between this xp and this LP. So xp contains functions, whereas this LP contains a class of function. So one element of LP represents many functions inside it, and this should be clear from this picture, right? So this whole thing, all the elements of here are in XP. So these are in XP, but this class is one element of LP. Okay, so that's the definition of LP, and on this LP space we define a norm. Okay, so in this way, so norm of equivalence class of f is equal to norm of f. So f was a function. Okay, so in case of this, you consider this f1, f2 are belonging to this class of 0 function. So norm of f is equal to this norm of f, I mean the class of norm of f is equal to the norm of f, and f is 0, so this is 0. So norm of f1 is also 0, norm of f2 is also 0. Okay, in that way. So we define norm in this fashion, that norm of class of function is equal to the norm of the function, okay, from that class. So this, if you represent the class by f, so this is equal to norm f is equal to norm of g. Okay, so for a, if g is related to p, so any element from this class you choose, calculate the norm p, what I have defined above, okay, and then that will be norm of the class f. Okay. Okay, so now you can check that this LP is also a vector space with respect to this pointwise addition and scalar multiplication. And this you see, I mean from the definition only it is clear that this norm of P is constant in one equivalence class, the way it has been defined, that if you choose, so this is one equivalence class, say there are other equivalence, so these are the partition. On this equivalence class, this norm of Fp for any function here is the same. Okay, so if you choose some g here, so suppose f1 and f2 belong to this class, then norm of f1 is equal to norm of f2 for any function belonging to this class. Okay, okay, and this is what we define by as class of norm of class. This is equal to f1 class. Okay, and you can see here that this, if class of f is 0, I mean norm of class of f is 0, then that would imply f is 0 almost everywhere, and this implies that this class f is nothing but the class of 0. Okay, so now on this space it is a norm. Okay, so on LP space, the functions what we defined earlier, that p function, infinity function, all those things are norm on this space, on this LP space. Okay, so this LP with this norm P is a normed linear space. Okay, that it is a vector space and it has a norm on it. Okay, okay, so do you have any doubt so far? Okay, if there is no doubt, let's proceed further. So I'll just list down few examples. So this example is nothing but the Lebesgue, I mean the usual thing what we have seen. So consider this measure space. Okay, then this is denoted, the LP space will be denoted by LP of x. So x is here AB, so LP of AB. Okay, and this M1 is the Lebesgue measure. So this is the collection of measurable function. So again, this is not just a measurable function, but class of measurable function. We generally write it as a function, but it is, the elements are not just a function, but it is a class of functions. Okay, so collection of class of measurable function, I mean. Okay, you understood what I said. So we know that it is a class of measurable function, but when we talk, we generally say it is a set of collection of measurable function. So instead of this collection of measurable function, you can write it collection of class of measurable function. Okay, where the class are the equivalence classes corresponding to the equivalence relation, almost everywhere relation. Okay, that f is related to g if f and g are almost everywhere equal. Okay, and this is the norm what we define on this space. So this is the usual, I mean the way we have defined so far, it's similar to this. So here p is in 1 and infinity. Okay, so I mean here we are just taking the Lebesgue measure, nothing special. But for the next example, this is quite interesting. So now consider some x equal to 1 to n. Okay, so this is just 1, 2, 3, 4 till n number you have in x. So this is subset of natural number. Okay, and you consider the power set of x as the sigma algebra, and mu is the counting measure. Okay, then this, if you take any function f defined on x, so x is 1, 2, 3, so f is a function from 1 to n to real number, right? So this is the function. Now this function is nothing but, I can write this function as a tuple, right? So this function I can represent it in a different way. as f1 as a tuple f1 f2 till fn, right? I can write this function in this way. I mean, just to, so these two quantities mean the same thing. So this means that what is the, so the function will be determined by what value the function takes on 1 2 3 and so on. So this function can be represented in this form, right? Okay, so any function can be identified as a tuple this. Okay, now consider this LP of mu. So we have to understand what this space is. Okay, so this is our concern. So you can see that this LP space, which is the collection of measurable function. Okay, now, okay, before going to this, let me just tell you one thing, that if you say f is equal to g almost everywhere, this means that measure of x such that fx is not equal to gx is 0, right? This is what it means, that f is equal to g almost everywhere. Now since we are in counting measure, okay, if f and g are almost everywhere equal, this means that mu of this set is 0. This means when we are mu of e equal to 0, when we are in this mu is counting measure, this means that e is empty, right? Because counting measure means if it is, say, it will be either 1. So counting measure means how many elements are there. So mu of e is equal to 0 means e has no elements. That means e is equal to 5. So when mu of such thing is 5, this means fx is equal to gx for all x. So here almost everywhere is same as talking of everywhere. Okay. So almost everywhere means at each point they are same in this context when mu is counting measure. Okay. Okay, I mean that's just a point what I wanted to make it here. Okay, so now this LP space, I am saying that this is just Rn. Rn in the sense that you can identify any function as a tuple of n entries. Okay, so this LP is Rn, and the norm, LP norm, what is this norm? You will have to check. Okay, so just take any point x from here. Okay, so you know what is this thing. So LP norm means norm of f, P norm means it is integration over x mod of fp whole raised to power 1 by p. Now when we are in counting measure, this integration is nothing but summation, right? So this is summation x in x mod fp, and here mod of fx, right? This is the definition of, I mean, this is what we have seen, that when we integrate with respect to counting measure, it is summation. So this norm of f is nothing but norm of this summation of fx raised to the power p whole raised to power 1 by p, where x is in x, right? And here x is what? This x is 1 2 3 4 5 6 like that. So here you can rewrite this as f of n, where n is from 1 to capital N, right? So this is the norm. Okay, so that's why what we have written, that LP of mu is Rn, where the norm is given as this thing, that summation of, so x, suppose x is x1 x2 till xn. So norm of x with respect with when p norm of x is nothing but summation of each of the xi's raised to the power p and then 1 by p, and for p equal to infinity, this is nothing but the maximum of these things. Okay, did you get this example? I mean, the second example. Okay, so now you can actually, instead of just talking for this n, I mean just finite set, you can talk of the whole natural number. So now this is your x, whole natural number, this power set, and this mu is counting measure. In this case, instead of just finite sum, you will have infinite sum. Okay, I mean the similar argument will work here, and instead of taking this maximum, you have to take supremum. Okay, because now we have a sequence of, so this LP space, where it is LP space is the sequence of real sequence equipped with the following norm. And you also know that this is denoted by this one. So this LP of R is the space of sequence as xn such that summation mod xn raised to the power p 1 by p is finite. Okay, so I think you must have seen this in the metric spaces chapter. Okay, so this LP is a particular example of LP when you take counting measure. So when you take counting measure, this and this are same. Okay. Okay, so now you have this property of inclusion. So what it says, that if P is greater than Q, then LP is contained in LQ. Okay. So for example, P equal to 2 you choose, the L2 is contained in L1. So this means that contain, and this is called continuous inclusion. Okay, so what it means I'll tell you. So this means that there are two things. First thing is that LP of mu, okay, the LP space is contained in LQ space. That if you choose any function which is P integrable, then it is Q integrable. When we are P and Q are in 1 and infinity, so it is not infinity, then we are saying. Okay. And the second one is that continuous means that norm of f of Q is less than equal to C times norm of f of P. Okay. If this relation is there, then we say that it is continuous inclusion. So what it means that, I mean, this continuous inclusion itself tell that this is true. I mean, this implies this. Okay, so I mean, you can remove this quantity. So maybe you can just cut this off. I mean, okay, so this is not, from here only you will get this thing. Why? Suppose the LP norm is finite. So if this is finite, then obviously this is finite, because this is less than equal to this. So if this is finite, then this is finite. So it says that if function is P integrable, that means if function lie here, then that function is lying here as well. Okay, so this is implying this. So in continuous inclusion, we say that this sort of inequality is there. Okay, and this is true for all f in LP. Okay. Okay. Okay, so we have, when P is larger, the space is smaller. That's all it says. That when, so you see that 1 is less than equal to 2, so L2 is contained in L1. That means the space of two integrable function is smaller than the space of one integrable function. Okay. Okay. Okay, so this is one example. And okay, the main restriction is that the space should be finite. Okay, it should not be finite, it should be sigma finite. Okay, so I think here is a typo. So it is true for sigma finite measure space. In particular for Lebesgue space it is true. No, sorry. No, it's right, it's for finite. So for Lebesgue space, Lebesgue measure, it will be true, but when the domain is bounded. So when x is 0, 1, then this is true with Lebesgue measure. But over R, this is not true. Okay. Okay. So the above true is not true for infinite measure space or even sigma finite measure space. I don't think this is true. Okay. So for example, you consider this one. So okay, so when we are considering infinite measure space, let us take this space n. Okay, I have written it here. So consider this space n, p and mu. Okay. In this case, LP is nothing but LP, right? LP of R. The sequence of, I mean the space of sequences, real sequences. So I mean this we have seen here, right? So this LP is nothing but this LP, small LP. So you can clearly see that summation 1 by n square, this summation, this is finite, so the root is also finite, but summation 1 by n is infinity, right? I mean this is not convergent, this is divergent series. So this 1 by n belong to L2 space, but it does not belong to L1, right? So L2 is not contained in L1, but here what we have seen, that L2 is contained in L1. So this is true when mu is finite. In this case, this mu is counting measure is infinite measure space or sigma finite measure space. So for this is not true. Okay. And in fact you cannot say the other way around as well. From here you might have seen that okay, L2 is not contained in L1, but L1 of mu seems, I mean, I'm not saying that this proves it, but it seems that this is contained here. I mean, okay, you have one example 1 by n. So if you choose 1 by n square, you can see that 1 by n square is in L1 and 1 by n square is also in L2. Okay. So the question is the converse true? I mean, the reverse inequality, is it true? So we have seen that L2 is not contained in L1, but is L1 contained in L2? This is the question. So for this space, this is true, that L1 is contained in L2. So if summation of xn is finite, mod xn, then this would imply that summation mod xn square is also finite. So if it is in L1, it is in L2. When we are in counting measure, when we are talking with this space. Okay, but in general it is not true. Okay, so this is what it says, that here I have written. So this, here we have seen the other way around, that if P is large, then the space is small, right? If P is larger than Q, then LP is smaller than LQ. LP is subset of LQ. But here the reverse is true, that if P is smaller than Q, then LP is smaller than LQ. So LP is contained in LQ. Okay. So this is when we are talking about n Pn with counting measure. So for this space, this is the reverse is true, and in general you cannot say that the reverse is true. So you can see this example. So 1 by root x belong to L1, but it does not belong to L2. Okay. Okay. Okay, so initially I was saying that why we are denoting with this infinity norm as supremum of this thing, right? So I mean, so what I'm saying, that when P was finite, we defined that this is Fp 1 by P. But for P equal to infinity, why we are defining it as infimum of this m greater than 0, such that mod f mu of mod f n, this is 0, right? So the question is why we are denoting infinity, I mean this infimum of such quantity as f infinity. The reason is that if you take limit p tending to infinity here, you will get this quantity. Okay, so this is the reason. So if f is in LP for all p, so that you have to understand that for all p, this is defined. So this should be defined for all p. In fact, after certain steps, so let us not say it is not defined, because we want to take limit as p goes to infinity. So even if p is not defined for 1, so suppose there exists some n naught, after which, so if f belong to LP mu for all p greater than equal to n naught, then also this is true, and I will prove this. Okay, so this I will prove in some exercise problem. I have chosen this type of problem where I will prove this. So if you have that f belong to LP for after certain stage, then you can prove that the limit value is actually f infinity. Okay, and that is the reason why we chose this notation, I mean this definition as infinity, because this quantity converges to this quantity. So this converges to this one, and that is why we define this as f infinity. Okay. Okay. Okay, so there these properties are that this LP space is a Banach space. So Banach space means any Cauchy sequence you take here, it will converge, it will be converging. So okay, so here what do you mean by Cauchy? And so let me just write it 1 or 2 lines. So LP with this norm, you have seen that this is a normed space. Now when I say Fn converges to f in LP, this means that norm of Fn minus f, P norm, is converging to 0. Okay, so you remember that Xn converges to x means that mod of Xn minus x is less than epsilon for n greater than equal to n. In other words, it means that xn minus x converges to 0 as n goes to infinity. Okay, this is what it means for real sequences, right? So here this mod is replaced by this norm, and again I mean similar thing. Okay, so in the similar way you can define the Cauchy sequences as well. Okay, so so this LP space is a Banach space. That means any Cauchy sequence in LP is a convergent sequence. Okay, and then if you have Fn converges to F in LP space, then there exists a subsequence of Fn such that Fn converges to F almost everywhere. So if you have LP norm convergence, then almost everywhere convergence is also there. So you remember that in DCT you proved that if Fn converges to F almost everywhere, and if Fn is bounded, then you show that integral Fn mod Fn converges to integral mod F. Like this type of thing you have shown, right? Or you showed integral Fn converges to integral F, but you can also show integral mod Fn converges to integral mod F. Okay? Because Fn converges to F means mod Fn also converges to mod F. So you have shown this type of thing. Now the converse is also true. This is telling you. So for p equal to 1, it says that if Fn converges to F in p, okay, so I mean, so you actually saw this also. So let me write, you saw there that this Fn converges to F is equivalent to saying that Fn minus F converges to 0. That means Fn minus F L1 norm converges to 0. Okay, this theorem is saying something converse, that if Fn converges to F in L1 norm or in any LP norm, then Fn converges to F almost everywhere. But Fn does not converge. There exists a subsequence such that that subsequence converges to F. Okay. Okay. Now, now this says, this is what I was saying here, that Fn converges to F in LP. This means that norm of Fn minus F P norm goes to 0, right? As I have defined here. But this is equivalent to proving that norm of Fn converges to norm of F. Okay. So if Fn converges to F, so there are 3 points. So Fn converges to F. So this is important assumption. So where is this? So see, Fn is a sequence almost everywhere which converges almost everywhere. So this is important assumptions. Okay. So this you need. So if Fn converges to F pointwise almost everywhere, then Fn converging to F in LP is equivalent to saying that norm of Fn converges to norm of F. Okay, so this is an equivalent definition of convergence. Okay. Okay, so that's all. So do you have any doubts regarding the whatever I have said so far? Then we'll move to some problems. Is everything fine till here? Okay, so now let's move to some problem. Okay, so we'll start with this computation of this derivative, so Radon-Nikodym derivative. So let's start with this problem. Okay. So let me recall what this mu plus and mu minus was. So this mu was a sign measure. So this is a sign measure. You define mu plus of E to be mu of E intersection A. Okay, so this A and B are coming from, so this A is nothing but the Hahn decomposition, and mu minus of E you defined as minus of mu of E intersection B. Okay, so this was the definition. Now you have to calculate d mu plus by d mod mu, right? So if you try to, so if you recall what was this derivative means, so suppose this is some function f, okay, then this means that mu plus of E is equal to f times d of mod mu. If I get this type of inequality, then I say that f is d mu plus by d mod mu, right? I mean, this is what I mentioned earlier, that this is what Radon-Nikodym derivative is. That if you get some function f such that mu plus of e is equal to f d mod mu, then f is d mu plus d mod mu, right? So this is the derivative. So you have to find what is this f. Okay, so the question is find f. Okay, so our goal is to find this function f. Okay, just one more thing before going to this, you just try to recall this thing. I mean, it's easy, so you don't need to recall also. You can check it here, that mu plus is absolutely continuous with respect to mu, and mu minus is absolutely continuous with respect to mu. So this I think I must have mentioned in the last session, and this is trivial to check. There's nothing special here. Okay, so I'll just leave this. Okay, so now this is sensible, so it's sensible to talk of this quantity. That's all what I'm trying to say. Okay, so now let us try to see what will be this function. Let us try to compute. Okay, so let E belong to this measure space S, sigma algebra. Then mu plus of E, from the definition it says that it is mu of E intersection A. So now this is nothing but, what is mu? Mu is mu plus minus mu minus. So it is saying mu plus of E intersection A minus mu minus of E intersection A, right? Now you try to understand that this will be 0. Okay, so my claim is that this is 0. Why? So recall, what is mu minus of some set? It is minus of mu of E intersection B. So this quantity, okay, so this quantity is mu. So I'm just using the definition. This is minus of mu E intersection A intersection B, right? And you know that A and B are disjoint. So this is minus mu of phi, and this is 0. So this quantity is 0. So now I can add this quantity as well. So this is mu plus of E intersection A plus mu minus of E intersection A, right? And this is nothing but mod mu of E intersection A, right? Since mod mu is nothing but mu plus plus mu minus, right? Okay. Now so this mod mu, if you want to write it, what this is nothing but integration of 1, okay, over E intersection A over d of mod mu, right? Now you see what here we wanted. So okay, so I have not mentioned it here, but here E should be there, I mean E. So this we are looking for the function f such that this thing happen. So you can rewrite this as chi of A, okay, d of mod mu E, right? You just try to check. So what it says that you are integrating chi of A, I mean 1 on, so this was your x, right? So this is x, this is A, this is B, and this is your, let's say this is your set E. Okay, so this one is your E. So integration of E intersection A, right? This part. And this integration, okay, so if you want in other way, you can also write in this fashion if you want. Okay, I mean it's fine. So this is nothing but chi of x. Okay, so or 1 is fine, I mean, whatever you feel, right? It's the same thing. So what it says that you are integrating 1 over this area, and when you integrate this E over this chi of A, so if you want you can calculate here that chi of A d of mod mu over E. What does this mean? This means that you are integrating over x chi of E, right? And chi, so this is your function, so this is your function, and d of mod mu. Now this is nothing but x chi of E intersection A, right? Because if you choose any point x from the intersection, this is also 1, this is also 1. If you choose something outside the intersection, one of them will be 0. Okay, so that's why, so these two are the same thing. Okay, so this is the calculation. So this is the mathematical thing, otherwise you can understand from the figure itself. okay, that you are integrating over E intersection A. Now since you want in this form, okay, that's why you have to include characteristic of A inside. That is, it will be taking value 1 when it is A, and when it is inside E as well, right? So what this quantity means, that same this, that if you are integrating on the points which is lying in A as well as in E, okay, so that's all this quantity means. So you have written this mu plus of E as integration of some function, okay, over E with respect to the measure mod mu, okay, and this is what we wanted. So let me just, okay, so this d mu plus by d of mod mu is equal to the characteristic function of A, okay. So if you want to write pointwise, is equal to chi A of x, okay. So this is the derivative of this mu plus. Similarly, and this I am not going to do, but you can prove that d mu minus of d mod mu of x is equal to chi b of x, okay. In a similar fashion you can prove this as well, so you can try this, okay. Okay, so I hope this is clear, right? Or do you have any doubt?
Yes, sir.
Okay, so now let me go to the next problem. Okay, so in this problem you have this nu is a sigma finite sign measure, okay, on this, again this measure space n and power set of n, and mu is a counting measure, okay. Then you have to, then I mean this I will prove that the first thing is proving that nu is absolutely continuous with respect to mu, and it's quite easy. So proving this means that let mod mu of E is equal to 0 for some E belonging to the power set of n, okay. Now what does this mean? This means that mu of E is equal to 0, and this means since mu is counting measure, this means E is phi, and from the definition of a measure you know that nu of phi is always 0. So nu of, for any measure nu, 0 by definition, okay. So this proves that this nu is absolutely continuous with respect to mu, okay. When this is absolutely continuous from, and both are sigma finite, right? So from, so since mu and nu are sigma finite, okay, and nu is absolutely continuous with respect to mu, so by Radon-Nikodym theorem there exists a measurable function f such that this nu of E you can write it as f, right, and d mu over this E, right. So there exists a measurable function f such that this thing happen. So this is known to you. That now the question is what this f will be. So the question is to find this f, okay. So that's the question, okay. Now so let us try to start with this nu of E. What is nu of E? So nu of E, if you look at this, this is nothing but integration of E of 1 over d nu, right? This is there. Now you can write this E, so you try to, so where is this E? You see E is in this power set of n, so that means E is some subset of natural number. So let me just mention it somewhere, that E belong to the Pn, right? So that means E is subset of natural number. Okay. Why I am writing this just for the notation purpose. So what I can do, E, I can write it. So I mean the point is that E can be written as disjoint points, right? So E, so let E, so let me write it here. So E is subset of N. This means E is countable. Okay, and in fact you can write E as union, disjoint union of, so let's say okay, so I mean let E equal to x1 x2 and so on. Okay, it may be finite, it may be infinite, so we don't care. So my main point is E, I can write it as disjoint union of xi's. Or okay, I mean just I'm writing I. Okay, so I belonging to some index set. Okay, it can be finite index set, it can be infinite index set, that's it. So this E I can partition in this way. So I can write this E as the sum of such integrals. So E I can write it in this disjoint form. So I can write this as I belonging to this index set I, integration over xi. Okay, so instead of this I can even write xi belonging to E if you want. Okay, such that over 1 d nu, right? I hope so far it's fine. Okay, okay. Now okay, one thing, let me just mention it somewhere. So just a second, I'll just mention it here maybe. Okay, now you see what this integration is. Okay, so suppose E I am writing in this way. Now here you are integrating with respect to counting measure, right? So you can write this nu of E as, so this integration with this counting measure will be a summation. So it will be summation over, so this E is a subset of natural number, so I am writing this by n belonging to E, okay, and f of n, right? This is the integration with respect to the counting measure, it is a summation, right? So here what we can do,
Sorry.
Yeah.
Can I sit here?
you can sit, I mean it's not a problem, but you cannot write, that's the only thing. You can sit here, it's not a problem. No, board I don't think it will make noise, right?
Oh,
uh, okay, so what I was saying, that this integration is nothing but a summation, right? So what you can do, so the main purpose is to find this f. Okay, so I was just rewriting this in this form. Okay, now okay, so here also if you want, I mean just to match with this notation, or here also you can write either xi, so better write xi here as well. Okay, okay. So here, so I am rewriting this xi belonging to E, integration of xi. Now notice one thing, this one I can write, so the main point is that I want to bring this mu on the integration, right? So the main question is that I want to bring this d nu, I mean I'll have to involve this mu here to get this f. So that's why what I'm doing, I'm writing this one as integration of xi, okay, with d mu. Why? Because this is mu is the counting measure, so the integration would be mu of singleton xi, and mu of singleton xi is 1, right? It is just containing one set, one element, and d nu, right? So this is mu of the singleton xi, which is 1. Okay. Now using the Fubini theorem you can interchange the this mu and nu thing. Okay, so what you can write is summation xi belonging to E, this xi d nu d mu. So this is by Fubini. Okay. Now what you can write, so now this quantity is nothing but, so this I can rewrite as summation xi belonging to E. This is xi, and this I can write it as nu of xi, right? And this is d mu. So this quantity I'm just writing as nu of xi, nothing special. Okay. Now again, okay. So I mean, so you can rewrite this as, so this I can rewrite as, so xi is over E, so I can write it as E. Okay. And okay, how should I write? So this is nu. Okay, so this xi is also in E, so this is nu of d mu. Okay, so this is the function f. Okay, and this function is taking the singleton's value. So I mean, I should not write it this way. So what I can do, okay, so I have this notation, right? So better write it this way. So what I can do here, you just take this nu of xi outside this integration, because this is some real number, right? This is some real number. So you just take this out, xi belonging to E. Then you write this nu of singleton xi, and this integration of this xi with respect to this mu, this is 1. Okay, so this is 1, so I can rewrite it xi belonging to E nu of xi. Okay, so this is another way of writing. So why I am writing this, just to match with this one. Okay, so you have got that nu of E, you know that it is a summation of f of xi, so you have got summation of nu of xi. Okay, so this f of xi is nothing but the measure nu of singleton xi. Okay, so this is the function. Okay, so this is one way, or I mean from here only you can write this nu and d mu over E. So this is another way. Okay, so whatever, I mean, in whatever style you are comfortable, you can check that. Okay. So if you want to look at in this summation form, then you just bring it further and write it in this way, otherwise this is fine. Okay. Okay, so did you get this problem, or do you have any doubt? Okay, if this is fine, let's move to the next problem. Okay. Now this question is saying that suppose you have LP space and LR space, then you have to prove that LP intersection LR, okay, so this P and R is lying between 1 and infinity. You have to prove that this LP intersection LR is a Banach space, the first thing. The second thing is that LP intersection LR is contained in LQ. Okay, I mean, this symbol is incorrect, so it should be this inclusion. Okay, yeah, so the inclusion LP intersection LR in LQ is continuous. So what it says, where Q is lying between P and R. So what it says, let's see. Suppose F belong to LP intersection LR. That means it belongs to LP. So suppose P is like this. So P is here, R is here, right? So I mean according to this. So F is belonging to this space, I mean corresponding to this, and F is belonging to this also. Then what this inclusion is saying, that F will belong to all the numbers, I mean corresponding to spaces corresponding to the numbers lying between this. So suppose you choose some here, some Q1, Q0, then it will tell you that F will belong to LQ0. If you choose some Q1, then you can say that F belong to LQ1 as well. So this is sort of interpolation, that if the function lie here LP, and if the function lie here, then it lies in between the spaces. So if it has LP, LR, then in all the spaces between this P and R, it is there. So that this is what it says, that if the function is in LP and it is in LR, then it is in LQ for all Q lying between P and R. Okay. Okay, so this is the question. Now let us look to the solution. Okay, So let us first prove that LP intersection LR is a Banach space. Okay, so for this is the norm for this space. So LP intersection LR with respect to this norm is Banach space. Okay, so just choose any Cauchy sequence. So let Fn be a Cauchy sequence. Okay, so I'm saying let Fn be a Cauchy sequence. Okay, now I'll prove that Fn is Cauchy in LP and LR. So this Fn is Cauchy in LP intersection LR. Okay, now let epsilon greater than 0. Okay, then just a second. Yeah, so then for okay, then there exist, I think it was correct, just a second, there exist n not belonging to n such that okay, norm of Fn minus Fm. Okay, so then for, let's say, then for 2 epsilon, so since it is Cauchy, I mean Fn is Cauchy in LP intersection LR, so for 2 epsilon greater than 0 there exists n naught in n such that Fn minus Fm is less than epsilon for less than 2 epsilon for all n greater than equal to n naught. Now this would imply Fn minus Fm P norm plus Fn minus Fm Q norm is less than 2 epsilon for all n greater than equal to n naught. Right? Now this implies that norm of Fn minus Fm P is less than epsilon and norm of Fn minus Fm Q is less than epsilon for all n greater than equal to n naught. Right? Because if any one of them is greater than epsilon, okay, so we better deal with epsilon. So if any one of them is greater than epsilon, then this would imply that the sum is also greater than epsilon. So this proves that since epsilon was arbitrary, okay, so this proves that Fn is Cauchy in LP and okay, is it Q or R? R. LP and LR. LR, right? So this implies that since LP and LR are Banach space, this implies Fn converges to, so let's say Fp, so Fp is some function in LP, so F converges to F in LP and Fn converges to Fr in LR. Okay, since LP and LR are Banach spaces. Okay, now this means that, so let me start with this one. So my claim would be, so let me write that claim is that Fp and Fr are same. Okay, and same means since they are same, Fp belong to, so let's say this is F, some constant. So my claim would be that these two are equal, and equal would mean that this is in LP as well as in LR, so it is in the intersection. Okay, so let me just prove this. So see, Fn converges to Fp in LP, right? So this means there will exist a subsequence which will converge pointwise. So this implies Fnk converges to Fp pointwise almost everywhere, right? Now this Fnk is a subsequence of Fn and Fn converges to Fr in LR. So this implies, okay, so I mean let me write it here. So Fn converges to Fr in LR. This implies that the subsequence Fnk converges to F in LR, Fr. Now again this would imply that there exists another subsequence Fnkj which converges to Fr pointwise almost everywhere, right? and okay, so this is 1, and also you know that f and k converges to fp pointwise, so f and k converges to fp pointwise. This would imply that when any subsequence you take, that will also converge to fp. So f and kj converges to fp pointwise as well. So from 1 and 2 you can say that fp is equal to fr almost everywhere. Okay, so and this proves, so this implies that fp is equal, okay, so that's all. So the limit is same. Okay. Okay, so this proves that this is a Banach space, the LP intersection LR. Okay, so this proves the thing that you chose any Cauchy sequence and you prove that this converges to some function in LP intersection LR. Okay, now let's come to the next problem. So the next problem says that LP intersection LR is contained in LQ. Okay, okay, so let me just say this p, let me write it here. So 1 is less than equal to p less than q less than r less than equal to infinity. Okay, good. Okay, so let me just consider, I'll consider one by one. So case 1, let us consider then r is not infinity. Okay, so r is finite. Okay, so let me prove for this one, and then I'll go when r is infinity, and that is much easier. Okay, so I have to prove that f belong to LQ. So I'll start with f of q. Okay, so note one thing. So from here only let me just write one thing, that p is less than q less than r. This means that 1 by r is less than 1 by q is less than 1 by p, right? And everything is less than equal to 1 and greater than 0. Okay. Now this would mean that, so see, this is 0, this is 1, this 1 by r is lying here, 1 by p, 1 by q. So you can write this middle point as a convex combination of this one and this one. So what I mean, that you can, there exists, so I mean you can write in this fashion that 1 by q is equal to theta times r plus 1 minus theta times p, where theta is some point, so where theta is some real number which is lying between 0 and 1. So this is just the convex combination of 1 by r and 1 by p. Okay, okay. So now let us try to estimate the, what do we want to prove? We want to prove that f belong to LQ. So see, what we wanted to prove, that this inclusion is continuous. That means we want to prove is that norm of f q is less than equal to c times norm of f p intersection L. I mean this norm of f, right? This is what we want to prove. I mean not exactly this, but okay, some sort of this. So I mean we'll see what this right hand side will be. Okay, so we'll see what it is. So we have to prove some estimate of this sort. Okay, so this right hand side will be determined later on. It will have some exponents and everything. So let us try to prove this. So maybe I should write, this is my claim. Okay, you'll see what it comes. Okay, so main goal is to prove that this quantity is finite. So if the function is in LP and it is in LR, then it is in LQ. So you have to prove that this quantity is finite. That's it. Okay, so we'll start with that motivation and then we'll see that what is coming. Okay, so let me write in this way, maybe that would be a better thing. So to prove that if f belong to LP intersection LR, then f belong to LQ, that is FQ, which is integration x mod FQ 1 by Q, this is finite. Okay, this is what I want to prove. Okay, so let us try to estimate that. So let us see what this f of q. f of q, I can write it as uh, mod of f. So what I can do actually, I'll have okay, let's see. So I can write it as q times somehow I have to, so main motivation, okay, let me tell you the main motivation, that I want to bring write fq in terms of some power exponent of this times some exponent of some exponent here, and then I'll prove that this function, I'll use the property that this, using this I'll show that this is belong to some L R1 space and this will belong to L R2 space, using the fact that the function is in LP and LR. Okay, so using that I'll prove that this is in this, and then I'll prove that since it is in this is finite. Okay, so that's the goal. So there's just some manipulation, just calculation manipulation is there, but this is the main idea. Okay, so what you can do here, you can actually use this theta what we have obtained here. So let me see, so it is q theta, and then you just subtract q minus q theta. Okay, then you will write this mod of f q theta and mod of f 1 minus theta q. Okay, now the idea is that you have been given that f is in LP. Okay, now just you will have to somehow write here, I'll use this Holder's inequality. Okay, so that will be coming, but let me just formulate this properly. So you will have to write f of you want here p. Okay, so p, okay, p is with 1 minus theta, so let me write it r. So this is r q theta by r. Okay, and let me write mod f 1 minus theta. Okay, and then p here, so p 1 minus theta q by p. Okay, okay, so I have done nothing, but I have just multiplied by r and divided by r. Here I multiply by p and p. I mean the motivation comes from here. I mean with p I have 1 minus theta and with r I have theta. So that's why I have done in this fashion. Okay, now notice this one. Okay, so now you just take integration everywhere. Okay, so this is our integration x, 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 x. Now just look at this f1. So this is f1. Let's say this is f2. Now see this f1, which is equal to mod f r q theta by r. Okay, I am saying that this belong to L r by q theta, right? Why? Since, just try to look at this one, mod f1 raised to the power. So you remember that f belong to LP means that mod of fp over 1 by p should be finite, right? So using this thing I can say, I mean this is the general definition, right? So here I am saying that this function belong to r by q theta. Why? Because f1 raised to the power r by q theta, if I do, what I get is mod f raised to the power r, right? And if I integrate this, you know that f belong to LR, right? So this is finite as f belong to LR. Okay, so this f1 is in LRQ by theta, right? Okay, as this, because of this. Similarly, you see f2 belong to L of this exponent 1 minus theta q by p. Why? As mod f2 raised to the power 1 minus theta q by p, if I do, what I get is, so with integration x, what I get is so this will cancel out, so you'll get mod f raised to the power p. So that this is also finite as, so since f belong to LP. Okay, so you know that these two quantities are finite. So f1 is in L r by r q by theta, and f2 is in L1 by 1 minus theta q by p. Okay, now try to recall this Holder's inequality. So as I mentioned there, that if a function f belong to LP and G belong to LQ, then and 1 by P plus 1 by Q belong to is equal to 1, then this norm FG L1 is less than equal to norm FP norm GQ, right? So this is the Holder's inequality. So Holder's, okay. So what I proved so far, that this F1 is in LR by RQ by theta, F2 is in 1 minus theta by Q by P, okay. So now let us check that. So this is 1 by P plus 1 by Q is equal to 1. So let us check 1 by this plus 1 by this, is it 1 or not? So are they conjugate exponent? Okay. So let us see, 1 by R by Q theta plus 1 by 1 minus theta Q by P. This is just a second, there's something wrong, right? I think this is okay. This is P 1 minus theta Q. This is P by 1 minus theta Q, right? P, then we have 2 1 minus theta, P by 1 minus theta Q, right? So if I take this P by 1 minus theta Q, if I do this, I'll get Q theta by R plus 1 minus theta Q by P, right? And if I take theta common, just a sec, so here if I take theta common, Q common, then what I have, theta by R plus 1 minus theta by P, right? And see what this was, where have I written, yeah, theta by R plus 1 minus theta by P is 1 by Q. So this is 1 by Q, so it is Q times 1 by Q, which is 1. So this R Q by theta is conjugate exponent of this one, right? So I can use Holder's inequality. Okay, so by Holder's inequality, what I can write, mod FQ is less than equal to F1, okay, F1 rest in R Q by theta into F2 was in P 1 minus theta by Q, P 1 minus theta Q, okay. So this is nothing but, so this is mod F1 R by Q theta raised to the power Q theta by R, and this is X mod F P by 1 minus theta Q over 1 minus theta Q by P, okay. And as I mentioned here, that mod F1 raised to power R by Q theta is nothing but mod FR, right? So this is mod FR, so this is X mod FR by Q theta by R, and this is X mod F P 1 minus theta Q by P, right? Okay, now I can rewrite this as 1 by R and this power Q theta, and this I can rewrite as 1 by P 1 minus theta Q, right? Now you see, this is nothing but R norm of F. So this is F R and this is Q theta, and this is P norm of F, P 1 minus theta Q, right? Okay. Now to get, so this, what does this show? This shows that this is finite, right? So you know that this is finite, this is finite, because F is in LR, F is in LP. So this is finite, so this is finite. Okay, so we are done. That inclusion is clear, but let us try to move a bit further. Okay, just to just to write this one. So as I mentioned in the very initial thing, that I have to prove continuous inclusion. That means norm of fq should be less than equal to c times norm of q and norm of r, and some involving this thing. Okay, so I'll have to see what this is coming. So let us write this. So what again? So to get norm of fq, I'll have to define, I mean take power of 1 by q. Okay, so this x mod f q raised to the power 1 by q is less than equal to norm f r. So 1 by q if I do, I'll get theta, and norm f p 1 minus theta. Okay, so you got this inequality. Okay, so or maybe let me write in short form. So what you have got is norm of f r is less than equal to norm of p, sorry, this is q, norm of r theta, norm of f p 1 minus theta. Okay, so this proves that LP intersection, so this proves LP intersection error is continuously embedded in LQ. Okay, and you can actually find this theta. Okay, so once you have this P and Q, so recall what this was. Okay, so if you want, you can calculate this theta. So recall this, what was theta? So here this is the expression, right? So you had this one. From here you can calculate what is theta in terms of P and Q and R. So you see, so I can break it up as theta by R plus 1 by P minus theta by P. So you can write it as theta 1 by R minus 1 by P is equal to 1 by Q minus 1 by P, and this implies theta is 1 by Q minus 1 by P into 1 by R minus 1 by P inverse. Okay, so I mean instead of theta you can write this also. Okay, so this is what you get here. Okay, I hope this is fine. And this was a bit calculative, I mean just manipulation. As I said, the idea is this: you want f to be in LQ, so you want to estimate this quantity. Okay, you know that f is in LR and f is in LP, so you have to use this. So you have to write this mod f raised to power something alpha mod f raised to power beta. Okay, such that you can write this, you can show that this is in some L, I mean LQ1, and you can show here that it is in LQ2. You prove that Q1 and Q2 are conjugate exponent, and using the fact that f is in LP and f is in LR, so using that you can prove this and this. Okay, and then you can proceed. Then use Holder's inequality, you will get that stuff. Okay, so I mean the manipulation is just at this level, that's it. Okay, so you can try these questions. I'll try to discuss in the next session. Okay, so you can try this. I'll see in the next session. I'll solve these problems. Okay, so do you have doubts so far, I mean in this session? Okay, if there is no doubt from this session, then maybe let's stop here.